Hello everybody, Chapter 5, Lesson Bravo, Logarithmic Functions and their Graphs. Our objectives for this lesson are the connection between exponential and logarithmic functions, evaluating logarithms with and without a calculator, properties of logarithms. I take that back. We're going to go over some of the properties of logarithms, but we will not be expanding and condensing until lesson C, which will be upcoming in the next video. Then we're going to graph some logarithms and maybe do an application at the end. So let's go ahead and get started. So a logarithmic function, by definition, I'm just going to read directly from my notes here. For x greater than 0 and a greater than 0, as well as a not equal to 1, the logarithm y equals log base a of x, that's how we would read it, log base a of x, is a function if and only if x equals a to the y. So the key to understanding logarithms is understanding, that was funny, that an exponential function and a logarithmic function are inverses of each other. So let's say I have 2 to the x, and I have log base 2 of x. Those two are inverses of each other, and it can be seen that way in many different ways. Algebraically, we could solve that. We could also do that just visually or geometrically, as we'd call it. But the two functions, an exponential and a logarithm of the same base, are inverses, provided that the inverse transformations are performed on each one. So let's go ahead and look at solving. We'll get into more of that as we graph later on in this lesson. Let's solve for the variable presented in each logarithmic equation. So using this idea, I can solve log base 2 of 8 equal to y. And I can put this in exponential form to understand that better. So I'm going to take my base 2 to my exponent y and set that equal to 8. All right, I know just based on algebra that 2 to the third equals 8, therefore y must equal 3. In some cases, the numbers might not agree quite so well, and that's when we'll use a calculator. Okay, if you don't know the mental math to solving some of these logs, you can expect that a calculator will help you. So let's look at number 2. Okay, in the same way, let's use exponential form. So my base is 3, my exponent is y, my answer is 1. Any number to the power of 0 gives us 1, except for 0 to the 0, but that's for a different day. So y would have to equal 0. So log base 3 of 1 equals 0 because 3 to the 0 equals 1. So logarithms can be solved by using exponents or exponential functions. All right, let's look at number 3. 4 to the power of y is equal to 2. Well, I know that the square root of 4 is 2, therefore 4 to the 1/2 is equal to 2. Therefore, log base 4 of 2 is equal to 1/2. Thus, y equals 1/2. Okay, let's look at number 4. Okay, if you ever see a logarithm without a base written, right, what is it? Well, the base, if you see a log without a base, that is called the common log, and that's base 10. Therefore, 10 to the third power will equal x. Well, 10 to the third is 1,000. Therefore, x equals 1,000. Therefore, log base 10, the common log of 1,000, is equal to 3. Awesome. Okay, let's continue on. All right, if you see ln, okay, no logs present, but ln, this is the natural log, so you can think of it as log base e of x. Okay, don't ever write that. That's just a mathematical sin. But understand that this terminology, this notation, ln of x, represents log base e. Therefore, e to the negative 1 will equal x. You could leave it like that, or you could write it as 1 over e. Therefore, ln of 1 over e is equal to negative 1. Okay, let's look at one more here. Log base 5 of 625. Well, 5 to the y equals 625. I believe 5 to the 4th is equal to 625. Therefore, log base 5 of 625 is equal to 4. Okay, let's get to a couple of examples where we cannot mentally do the math in order to solve this. Okay, but let's think about what it would be, or at least with some number sense, estimate where this answer would be. So 3 to the power of y is equal to 30. Well, I know that 3 to the first is equal to 3. 3 to the second is equal to 9. 3 to the third is equal to 27. And 3 to the fourth is equal to 81. So I know that 30 falls between 27 and 81. And it's much closer to 27 than it is 81, so I would guess, about 3.1. Now, since we don't have a whole number answer, we would require a calculator in this case. So in order to evaluate, I want you to take a look at the screenshot of my calculator. I pressed the button, the math button here, and it showed up at the very top, and the first option is fraction, right? If I go up, it brings me to the very bottom, and I went to log base. If you press enter on log base, it pulls up some notation that looks like this on your home screen, where there's a blank here where I have my 3 and a blank where I have my 30. I input a 3, I input 30, I press enter, and it looks like I get what I thought I'd get, or at least close. As I see my calculator, I would go back to this answer and change it to 3.096. Of course, 3 decimal places if not told to do otherwise. So that's how we use a calculator to find a logarithm. Let's go ahead and look at another one. Okay, very similar. I wanted to show you this one. There's not much different in the process here other than just keystroke. Your calculator on your main, buttons and well, whatever. On your calculator, there's 2 buttons. If you're going to do a base 10 logarithm, which is the common base, that's this button. If you're going to do a natural log, that's the button right beneath it. If you have to do any other base calculation, then you're going to have to press math, go up, find log base, and do that work. But since this is a natural log, which is very useful in a lot of areas of math, I just press ln, plug in a 23, and I get this answer. I would lop that off right here and call that 3.135. Okay, now let's continue using these ideas and get into some graphing. All right, no graphing yet. We're going to do a little bit with properties of logs. A couple items just to be aware of. If you have a log of any base of the number 1, right, that would mean that a to some power equals 1. The answer will always be 0. Okay. If you have log base a of itself, that has to equal 1 because a to the first power has to equal a. So the first one is because a to the 0 equals 1. The second one is because a to the 1 equals a. Okay, of course I'm using these bases right here and these arguments right here. Okay, if you have log base a of a to the x, it will equal x because a to the x will equal a to the x. Okay. All right, and the last one, if you have log base a of x equal to log base a of y, then you can assume that x equals y. So let's use that in the problems below. Well, notice that I have log base 2 of x equal to log base 2 of 3. That tells me immediately that x has to equal 3. Since the bases are the same, there's no coefficients in front of the logarithms, we can stop right there. So x equals 3. Okay, and number 2 here, I've got log base 3 of 1 equals y. We can use that first property up there. 3 to the y equals 1, therefore y equals 0. Okay, the third one here, I've got 2 times ln of e equals y. All right, so if you if you strip away the 2 for just a moment, imagine it's not there. The natural log of e, let's do this off to the side. What is the natural log of e equal to? Well, that'd be, remember, this is base e, so that'd be e to the x equals e. Well, we get that by then saying that x equals 1. Therefore, if the natural log of e equals 1, then I have 2 times 1 equals y. So y must equal 2. Okay. There are other ways to do every one of these problems, but I would suggest using your knowledge, or soon-to-be knowledge, of logarithms and exponential functions in order to solve them. Okay, here's an interesting one, kind of goofy. This is just an exponential function. So let's say that I said 7 to the x equals y. How would you write that into logarithmic form? Well, that would be log base 7 of y equals x. Okay, so if 7 to the x equals y, then log base 7 of y equals x. So if 7 to the log base 7 of 14 equals y, then log base 7 of y, all right, now in my logarithmic statement, I'm getting those values from there, should equal my exponent. Okay, now since I have two bases that are the same, y must equal 14, so their arguments must be equal. Bottom line, if you have a to the log base a of x, we're going to talk about this again, is equal to y. We're going to talk about this again in lesson C. If you have anything of this form, your answer is just going to be x. Okay, your answer is just going to be x. We'll get into that more in lesson C. All right, let's look at another example. E to the ln of 5. Very similar. Notice that you have e to a log of its same base, so y would equal 5. Again, if that slipped by you, don't worry about it. We'll get to it more in lesson C. Okay, here we go. Yet again, I've got logs of the same base. Therefore, 625 has to equal 5x. If I divide by 5, I think I get 125 for x. Okay, some properties of logarithms. Let's keep on moving. Okay, I'd like to do some graphing here, so let's jump into exponential and logarithmic graphing. All right, I'm going to draw a rough sketch, okay? This is going to be the point 0, 1. This will be the point 1, 2. This will be the point -1, comma 1/2. Okay, so this is the graph of y equals 2 to the x. Log base 2 of x is an inverse function of 2 to the x. So if I analyze 2 to the x, its domain of 2 to the x is going to be all real numbers. And its range of 2 to the x is going to be greater than 0. Okay, so we can expect for a logarithm that is the inverse of an exponential function to have the domain and range of the original except flipped. So we can expect the domain of log base 2 of x to be the same as the range of 2 to the x. So we're going to have domain from 0 to infinity. So the horizontal asymptote on the exponential function becomes the vertical asymptote on the logarithm. And then what we see is that the range, of course, flips. So the range of log base 2 of x is all real numbers. All logarithms' ranges are all real numbers, just like all exponential functions' domains are all real numbers. Okay, so I'm going to take these points and I'm going to flip them. So I'm going to have the point 1, 0, flipping their domains and ranges. 2, 1, oops, I don't want it there. It's going to get in the way of the graph. And the point 1, -1. All right, so you can see the graph of this logarithm, and we sketched one earlier, is going to look like that. That would be a nice perfect vertical, or excuse me, reflection over the line y equals x. Okay, let's graph 3 to the x. Very similar. Here's 3 to the x. And points 0, 1, 1, 3, negative 1, 1/3. Log base 3 to the x. Vertical asymptote. Okay, this would be the point still 1, 0. This would be the point 3, 1. This would be the point 1/3, negative 1. This is log base 3 of x. All right, let's talk a little end behavior on any one of these logarithmic functions here real quick. The limit as x approaches infinity of log base 3 of x. Okay, it kind of looks, as I'm looking at this, as x goes to infinity, this graph looks like it might level off, but it never does, right? It just keeps going. Slowly, but it keeps going. Not like the exponential that takes off. It's just going to keep going slowly and go off to infinity. So its end behavior on the right will be infinity. However, the graph does not go off to the left, so I can't write left end behavior. But I can write the behavior as it approaches 0. But I have to say as it approaches 0 from the right, because the function doesn't approach 0 from the left. So the behavior as x approaches 0 from the right is negative infinity. And that'll be true of all logs. As they approach their vertical asymptote, they'll either go off to infinity or negative infinity. Let's look at the natural log. Of course, we know what e to the x looks like. Again, general sketch, not accurate. Don't shame me. This would be the point 1e. This would be the point negative 1, 1 over e. Okay, so it's got its horizontal asymptote here and here at y equals 0. The graph of e to the x. This is the point 1, 0. This is the point e1. This is the point negative, 1 over e, negative 1. Okay, there's our graph. Again, vertical asymptote at x equals 0. So the vertical asymptote location will only change if we have a horizontal shift. Okay, stretch doesn't matter, just a shift. So we're going to talk about domain and range in a little bit regarding both the exponential and the logarithm. So let's move on. Okay, so I'm going to graph both of these logarithms here, but the first thing I'm going to do is I'm going to figure out what its exponential inverse would be. Okay, so let's go through the process of finding an inverse. Remember, the first step that we use is we switch x and y. Okay, so I switch x and y. Now I want to solve for y. So I'm going to negate the right side. And in order to rewrite this, I'm going to use the switch from logarithmic to exponential form. So I would see that y minus 3 would equal 2 to the negative x. Okay, therefore y would equal 2 to the negative x plus 3. Okay, so our inverse, right, this is our inverse function. I'm going to sketch a graph of 2 to the negative x plus 3. So I'm going to plot x values of negative 1, 0, and 1. Let's see what we get for 2 to the negative x plus 3. So if I plug a negative 1 in there, I get 5. If I plug a 0 in there, I get 4. If I plug a 1 in there, I get 3.5. Okay, so let's plot these. Negative 1, 5. Okay, 0, 4. And 1, 3.5. Oops, bumped the screen there. Or 7/2, right? So let's talk about real quick about the domain and the range. Well, the domain of this function, domain of, I'll call this y inverse just for the heck of it, is all real numbers. We know that. right? Range of y inverse. There's going to be a horizontal asymptote where our vertical shift took place, right? So we shifted up 3 units, as you can see right here. So our horizontal asymptote went from 0 up to y equals 3. Therefore, what I know now is that if there's a horizontal asymptote at 3 for its exponential inverse, there's got to be a vertical asymptote at 3, x equals 3 for the original graph. Okay, now this is kind of funky, okay, but there's not only been a horizontal shift 3 units to the right, but there's also been a vertical reflection in this logarithm. So the log won't look like it normally does. It's going to flip-flop points here, and as we approach 3 from the right, it's going to increase to positive infinity. You'll see what that looks like in just a second. So let's plot the following points, right? We know that if negative 1, 5 is on the exponential function, then 5, negative 1 will be on the logarithmic function. Okay, so let's plot that. 5, negative 1 would be here. Okay, if 0, 4 is on the exponential, then 4, 0 will be on the log. If 1, 3.5 is on the exponential, then 3.5, 1 will be on the log. Okay, so we're going to see a graph that looks just like this. And that makes sense, right? If I sketch the line y equals x, those two functions look like a nice perfect reflection along that line. So this would be the function y equals negative log base 2 of x minus 3. Let's try another one. How about natural log of x plus 2 minus 1? Let's first find the inverse. X equals ln of y plus 2 minus 1. So x plus 1 is equal to ln of y plus 2. Now we rewrite in exponential form. That's e to the x plus 1 is equal to y plus 2. Therefore, y is equal to e to the x plus 1 minus 2. Okay, so e to the x plus 1 minus 2. Let's sketch that real quick. So let's go x and e to the x plus 1 minus 2. There are other ways to do this. I find this to be the most efficient. Or you can just plot points. It's totally up to you. It just won't take shape quite as easily. If I plug in a negative 1, I get e to the 0, which is 1, minus 2, which is negative 1. Plug in a 0, I get e minus 2. Plug in a 1, I get e squared minus 2. Ooh, that's kind of yucky. Okay, let's see what that would look like. I could use my calculator, but I'm just going to go with negative 1. Negative 1 is a pretty nice number, so let's put that there. Negative 1, negative 1. Okay, first of all, as I look at this, this is going to be a exponential function shifted down 2 units, so I know I'll have a horizontal asymptote at negative 2. Y equals negative 2 there. And I've shifted my exponential function down 2 and over 1. Over 1 meaning to the left 1 unit. Or excuse me, yeah, to the left 1 unit. Okay, so where would 0, e minus 2 be? All right, so e is a little bit less than 3, a little bit more than 2, so that'd be like between 0 and 1 if I took e minus 2. So 0 comma e minus 2 would be right in this area. Okay, e squared is going to be a little less than 3 squared, so a little less than 9. So let's go with like 8 minus 2 would be right around 6. So 1 comma 6. Again, that's an estimation, but I would have positive 1 comma e squared minus 2. That's an estimation of that point. Okay, you could use your calculator to kind of help you figure that out. Okay, so that's what our function would look like. So now let's determine, based on the shape of that graph, what our logarithmic function should look like. So since this has a horizontal asymptote at y equals negative 2, our logarithmic function would have a vertical asymptote at x equals negative 2. So we would have a vertical asymptote right here. Okay. We're going to flip those 2 points on each of those, actually those 3 points. We're going to flip the x and the y values. So we would have points -1, -1, and e minus 2, comma 0, and e squared minus 2, comma 1. So -1, -1 is a nice point. E minus 2, comma 0 is going to be right in this general area. So this would be e minus 2, comma 0, and e squared minus 2, comma 1. So e squared minus 2, comma 1 we said was like around 6. So 6, comma 1 would be here, e squared minus 2, comma 1. All right, so our graph, ooh, this is going to be really interesting. It's going to look like that. That's really nice. So if I drew the line y equals x, look at that, nice perfect reflection about that line. Okay, so that would be the graph of y equals ln of x plus 2 minus 1. Now I make up for the estimation process by labeling in exact form. If you know what I mean, this labeling in exact form makes up for the sins of my estimations. Okay, my sketch is not perfect, but the fact that I've labeled all vertical asymptotes, all horizontal asymptotes, and at least 3 points on each function, I'm good to go. Okay, so make sure and pay attention to those details. Let's keep moving. Okay, a couple more slides here. This slide with domains and ranges and their restrictions, and then an application slide after that. So a logarithmic function range will have no restrictions, much like the domain of an exponential. What that means for you is that if there's vertical transformations going on, you don't care, right? The range isn't going to change. It's always going to go from negative infinity to positive infinity, but based on the orientation of the vertical reflection, potentially, left end behavior might be up to infinity, right down, or the opposite. Okay, but range, you never have to worry about any restrictions on range with logs. However, the log function's range, excuse me, that shouldn't say range, that should say domain. Domain will be naturally restricted due to the presence of that vertical asymptote. So much like the range of an exponential and its horizontal asymptote. So let's find the domain and range of each of these functions. All right, so I got an exponential function here. An exponential function's domain, all real numbers. Done. I'm not worried about it. Its range is different. Okay, so this exponential function is going to look something like this. Because of the -2 out front, end behavior will go down like this. Okay, now the horizontal asymptote, I haven't drawn this correctly, but the horizontal asymptote is located where the vertical shift ends up being. Okay, so this number out in front tells you what happens with the right end behavior. Limit as x approaches positive infinity of f of x will equal negative infinity. Okay, so if that's a negative value out in front for a, then you're going to get that end behavior. Therefore, our range would be from negative infinity up to, but not including 5. Okay, let's look at this one. Actually, I want to look at the exponential down here first. Okay, so we see positive here. That tells me that my graph of my exponential function is going to approach infinity to the right, and some horizontal asymptote looks like -2 as it goes to the left. Therefore, domain, again, not worried, all real numbers. Range, however, will be from vertical asymptote up to positive infinity. All right, let's talk logs now. Now, logarithm, its range, I'm not worried about. All real numbers, every time. Its domain, though, is going to be restricted based on its horizontal shift only. Therefore, since the original natural log has a horizontal asymptote at 0, or excuse me, vertical asymptote at 0, that means I want this thing's called the argument. I don't know why. Maybe because they thought about what they should call it. Ha, math joke. We always want the argument to be greater than 0, because a logarithm that hasn't been shifted does not exist in this direction. Okay, so to find the domain, we take the argument, x plus 6, very much similar in the same way, wow, that was redundant, as square roots. So we take this, greater than 0. Therefore, x has to be greater than -6, or we could say -6 to infinity. Okay, let's look at another example. Here's a good one. This log's been reflected vertically. Guess what? That doesn't matter at all. Its range is still all real numbers. Its domain is going to be based on the argument. So x squared greater than 0. X squared is greater than 0 everywhere except at 0. Right? So if I sketched x squared, I know this is going places. Oh my gosh, I can't get that to go through. There we go, that's better. It's greater than 0 everywhere except at 0. Right? The function x squared is greater than 0 everywhere except when x equals 0. Therefore, we would say from -infinity to 0 and from 0 to infinity. Or you could say x can't equal 0. That would be the domain of negative log x squared. Okay, last one. Again, vertical transformation makes no difference on the range or the domain for that matter. All real numbers. The domain would be based on the argument. So I'm going to subtract 3. So x is greater than, -x is greater than -3. When I divide by a negative, that takes out the negative signs on both sides and flips the inequality. Therefore, our domain is -infinity up to 3. Okay, guys, that's how you find the domain and the range of an exponential and a logarithmic function. Let's get to an application problem, and that'll be it for this lesson. Okay, this application problem, the memory model, students participated in a psychology experiment, attending several lectures on a subject, and were given an exam. Every month for a year after the first exam, they were retested to see how much information they retained. The average scores for the group are given by m of t. Okay, so let's talk notation real quick. M of t is equal to 75 minus 6 natural log of t plus 1, where t is in months. Okay, so here are the months. The first test was taken at t equals 0. The last test was taken 1 year later, which was 12 months later. So what was the original average score? Okay, so we plug in a 0. So if I plug a 0 in for m of t, I get 75 minus 6 ln of 0 plus 1. Okay, so that's asking what ln of 1 is equal to, right? That's important. It's a big one. That is one you always want to remember. ln of 1 is 0. Always will be. Okay, so this is 6 times 0, which is 0. So the average score on the first exam was a 75. What would be the average score 6 months later? So that would be m of 6. That's 75 minus 6 ln of 6 plus 1, which would be 7. And a year later would be m of 12, which would be 75 minus 6 ln of 13. Now, I don't know what the natural log of 7 is, so I'm going to need my calculator, just like you would. So 75 minus 6, 75 minus 6 ln of 7. 6 months later, the average score is a 63. I'm rounding. Okay, 1 year later, I don't know, take a guess. I'm going to guess in the 50s, maybe 40s. I'm going to do the same calculation, except with 13. Ooh, just under passing. 59.6. We're not giving it to him. Okay, so here you have it. There's applications. Lots of modeling coming up in our future. So hopefully this lesson went well. Let me know if you got questions. Have a great day.